Alright, this is video number 5 in our Unit 2, and this is when we actually start to getting into some new things. We'll take it step by step slow at the beginning, and you'll see in the 6th one and 7th one things will be ramping up quite quickly. So, got some new equations coming down the pipes. Let's take a look at where we're starting from. So, if I asked you for an acceleration equation, I sure hope by now the one I would get is acceleration is change in velocity over time. Now it is technically delta t there, but as we have been doing and will continue to do, we're going to drop the delta, because we're assuming it is our time interval. Because very rarely do we deal with the actual time interval in a problem. But what we want to do with this equation is we are often constantly rearranging it. So we're actually going to work with it now from a different form. So we're going to expand out the delta v so that we get v minus v naught all over t. And then we want to rearrange it for our final velocity. So just v. Not terribly tricky, something that we've been doing in the problems already. Multiply by t first, and now we want to add v naught to either side, and I'm quickly just going to shuffle the left side and right side so that I get v naught plus at. So this equation will become known as equation 1. It is exactly the same equation we've been working with. It's just arranged for a different variable from the get-go. So you can just start from this equation solved for our final velocity. In terms of using it, we've used it before, makes no difference. It's just arranged for an easier variable. So these two problems here are just more practice. We'll go through those in class. So, from a velocity time graph. So we just talked about velocity time graphs. Let's bring those in and get an equation coming from there. One thing that we can get is we can get acceleration from the slope. We can get the velocity from any point on the graph. But now we're also going to be able to get the average velocity just between 2 points and the displacement from the graph, not just from an equation, from the graph. So let's start with average velocity. As simple as it gets, if you're taking the average of something, adding it up and dividing by how many you had. So in this case, if we think about having VAV would be our two velocities that we often work with, final plus our initial, V plus V naught, and we're going to divide it by 2. It's as simple as that, and that's just the average velocity. So if we're looking at this example here, we're trying to find, so we're given V naught is 10 meters a second. V is 30 meters a second. We're given time is 5 seconds, and we're asked for VAV. So VAV is 30 meters per second plus 10 meters per second all over 2. 30 plus 10, 40 divided by 2. So that gives us 20 meters per second as our average velocity while that object is accelerating. So if the way to think about that is if there's a second car that's moving at 20 meters per second only, it will cover the same distance as something that is accelerating from 10 meters per second to 30 meters per second. So it's sometimes a useful thing to think about the average, because it'll help us calculate the displacement, which is what we're going to do right now. So we say here, so from a velocity time graph that represents constant acceleration, whether that's 0 or some number, the displacement is equal to the area between the graphed line and the x-axis. That might be a new idea, so let's actually take a visual look at what that is. If we have a velocity time graph here of a car traveling at a constant velocity of 30 meters per second, how can we find the distance traveled in 20 seconds? Now, let's do this one way that we know how to do it. Let's do this equation way. And then after, we'll compare it to using the graph. So in an equation, well, we're told that v is 30 meters per second. We know time is 20 seconds, and we're asked for d. This is the first equation we've ever learned when we're talking about motion. D equals vt. And so we get 30 meters per second times 20 seconds, and that gives us 600 meters. Okay, so we should be able to come up with this number from the graph. And hopefully you start to see a connection here. So when we're talking about area, and if we're looking at the distance traveled in 20 seconds, so that's going to be from 0 to 20 seconds. And so to do that, I'm going to draw an imaginary line here, straight up from 20 seconds to meet the line. So when I'm talking about the area between the graph line and the x-axis, that's the area in the time interval between the two. So that is all of this space here. Okay, well let's calculate that. Area. We're dealing with a rectangle here, so area is just going to be the length times the width, which is equal to what? Well, how long is this side, and how long is this side? It doesn't matter which you call length or width, really doesn't matter. The one side goes from 0 to 30, and it's got units of meters per second, so we can say that it's 30 meters per second long. And the other side goes from 0 to 20 seconds, so we can consider that 20 seconds long, because those are our units. These aren't units of actual length, we're just calculating an area here with different units. Okay, we multiply those two together, we get 600 meters per second times seconds will give us meters. Wait, that's the same displacement. We just came up with the same number. So our displacement is just calculated by finding out the shaded area of the graph. So that's from, in the time interval, from the line to the x-axis. If you can calculate that area, you can calculate the displacement of the object. Now it looks very simple for this problem because it has zero acceleration. Let's take a look at the graph on the next page. If our object is accelerating, would this also be true? Well, what I'm going to get you to do is to come up with an equation to do so. So you're going to come up with an equation for the displacement. And remember, displacement equals area. So if you find an equation for the total area, you will find an equation for the displacement. So do that, and then come back, and we'll move forward. Welcome back. So if you pause it and work through that math problem, that's fantastic. What you should get is our displacement is equal to, and this might be written a little differently from yours, but hopefully you can see that it is the same. Displacement is 1/2 times our v plus v naught, all multiplied by time. So that should be the equation you come up to. And this we will call equation 2. If you didn't come up with that, ask somebody in class to see if they can show you how they did it. So let's use this to calculate this displacement here. So we have v is 11 meters per second. V naught is 33 meters per second. Time is 20.0 seconds, and we're looking for displacement. Now you'll notice that displacement, we've stopped writing the delta there as well, And again, that's just because we're almost always talking about displacement, and it's always from 0 to somewhere else. So we're just simplifying our life a little bit. So let's write out our equation. Displacement is 1/2 times v plus v naught, all multiplied by time. So 1/2 times 11 meters per second plus 33 meters per second multiplied by 20.0 seconds. So you plug that into your calculator and then you will get 440 meters as your answer from your calculator. Now let's check sig figs on there, just so we know that we're doing things right. So if we added 11 meters per second plus 33 meters per second, that would give us 44, and that's both numbers are to the ones value, so that would stay to 44. And then multiplying that 44 has 2 sig figs multiplied by a number with 3 sig figs, so we end up with a number that should have 2 sig figs. And our answer does have 2 sig figs, so 440 is the correct final answer. We will go over some more problems in class, and as always, physics is awesome.